Section 75. Our objective is basically just the title of the section. You know, what we want to be able is solve those exponential and logarithmic equations, figure out how to do that. Now, logarithms, we know if we have to do something with them, we're going to have to snail shell. It's just like learning a new language. When you hear the first word in that language, it's like you pause and you think, what does that mean in English? You know, you're always translating it. It's the same thing with logarithms. We have to snail shell in order to translate it, to have it make any sense. So we're going to solve exponentials. We're going to solve logarithmic equations by using what we know. This Getting Ready says you are a winner on a TV game show. Oh, good for you. Which prize would you choose? And explain. And prize A is $10,000 a week the rest of your life. $10,000. Prize B, you only get a penny today, but tomorrow you get 2 pennies. And the day after that you get 4 pennies, and so on and so on. From what we've learned so far, which of these do we know we should be picking? The penny. Sounds awful, right? But we also know that with exponential functions, it's going to grow huge amounts. So let's just say we start with our penny. Just put this on the graphing calculator. There's day 1. So now the next day is a 2 and then a 4. So let's see here. We really just add 0.1 to get the 0.02. But then we see they're doubling it. So maybe I should start, multiplying this by 2. But if it's 1 cent, then 2 cents, then 4 cents, it also could be powers. Either way, let's just say I go with doubling it. So there's my doubling. And it takes a while. So, you'd have a few weeks here where you're not real, or a few days where you're not very happy. But now look what's happening. That's much more than $10,000 per week. Much, much more. And we went through that myth of the soldier and the strange request, where he said, bring me the chessboard with 64 spots on it, and I just want 1 kernel of wheat on the first one, and then double it for every other one. And it ended up being a massive amount of wheat. So at this point in the year, we know, hey, we should be taking prize B. I always think this is horrible because it's kind of like promoting the lottery, but it's not. What we're doing is we're trying to teach you, how to make those educated choices. And any equation that contains the form b to the cx, such as a equals b to the cx, where the exponent includes a variable, that's called an exponential equation. And this is what we've had before. I mean, when we were working on exponential equations, dealing with interest before, there'd be times when we had things like this. And we had to say, got to use Blinky. I don't know what to do with that. Well, today we're going to find out how to solve this by hand, and then use a calculator to get our final answer for it, for the amount of time that it would take to get $2,500 if you started off with $1,000 at 6% interest. So essential understanding down here says you can use logarithms to solve exponential equations. Yeah, that's what they're for. You can use exponents to solve logarithmic equations. Yeah, because they're inverses of each other. In fact, early on, we found out there are fewer inverses. When we see logarithm base 5 of 5 to the x, both of these bases are 5. It's not like to undo adding, you subtract. You only have to do some math to do that. We undo multiplying by dividing. This is, hey, this just totally undoes that, and it's gone. It's a perfect inverse. It just gives us x right back. That's the property that we want to use when we're solving these, because it'll be super easy to do. And now with that nice change of base formula that we have, we can punch any of this stuff into the calculator if we know that change of base formula. So on the next page it says, let's back up a second. We actually solved these a little bit earlier in this chapter. It said, solving an exponential equation using a common base. So we start with 16 to the 3x equals 8. I start thinking, okay, I'm supposed to use the same base, so I have to use a number that's small enough that if I raise it to a power, I could get 16 and I could get 8. Can you think of a number small enough that if we could raise it to powers, we could get an 8 and a 16? Maybe a 2. Now, 8, most of us know immediately is 2 to the third, so then you have to think, okay, how many more 2's would it take to get 16? And just one more, because 8 times 2 would be 16. So this is 2 to the fourth. But that's not all it said. It had a little 3x right up there. So then I think, okay, that's a power rule. When you want to raise a power to a power, what are you supposed to do with the exponents? Multiply. Yeah. So we need to multiply 4 times 3x, and that's going to be 12x. Now we did these earlier in this chapter. Does anybody remember how we solve it once we get to that point? Been too long. It was before spring break. Okay. The 2's are already equal. Do we care about the 2's? No, they're already equal. We need 12x to equal 3. That's the only way this is going to work. So basically, if this base is the same, we don't need it anymore. We need 12x to equal 3. And then that means we're just going to divide both sides by 12. And there's our answer. X should be 1/4. If it is, it should work. Very easy to check, by the way. Take a look at this problem. All we have to do is punch in 16 times 3 to the 1/4 power. And we'll know. Does that give us 8? So 16 to the parentheses 3 times parentheses, oops, not second, parentheses 1/4 is that 8. There it is. So gotta like the solving problems. It's always one of those things before you turn in your test, you can go back and just check it. Okay, do all my answers work that I have here? So now the next one is what's the solution of 27 to the 3x equals 81? And I think it's would be a good time for us to have some candy corners. So let's talk first about, let's see if we could start everybody out with a number that's small enough that you could raise it to a power and get both 27 and 81. What would that number be? 3. So everybody think 3. I'll pause this. 27, everybody seem to know that's 3 to the third. The problem is when you try to skip steps. I mean, you really shouldn't be skipping steps at this point. And when you do that, then it's like, okay, how do I get all this to work? Well, a power to a power is multiply, so this will be 3 to the 9x equals 3 to the 4th. And then the 3's, we don't need them. These 3's are already equal. We need 9x to equal 4, or this isn't going to work. And we divide both sides by 9. And we get 4 9ths. And that's our answer. And again, it is checkable. It's kind of a little monster to plug in. Some of you have the calculators that do the nice popping up and giving you a little rectangle to fill in with the power. That's actually a nice feature for this one, because it doesn't make it so messy. But it is checkable so that you can see whether or not it works or not, which is good. So why not just do this all the time? You know, why not just always get the same base? Because there are some numbers where we're not going to be able to make that happen. Let's say we have 2 to the x equals 7. 2 would be the obvious choice for a base. But if you raise 2 to the first power, you get 2. 2 to the second power, you get 4. 2 to the third power is 8. We just missed our 7 altogether. So if we can't do it that way, we need it another way. And that's where logarithms come in. So if we can't get those bases to be the same, logarithms work. That's what they do. So when the bases are not the same, solve an exponential equation by taking the logarithm of each side of the equation. Huge, by the way. We're so used to that it's one of those things we don't even really read anymore. With algebra, we know whatever you do to one side, you have to do to the other. It's a have to. So if I go back to my little 2 to the 7th, or 2 to the x equals 7, and I think about what I don't want to be there, I don't want that 2 there. Because while that 2 is there, I can't get to x. And x is what I'm supposed to be solving for. So I think, okay, it's got a base of 2. I should use a logarithm base of 2. But it's still algebra. So whatever I do to this side, I have to do the other. Now here's the fantastic news. Over here, these just cancel right out, and you get x. And on the other side, you just learned yesterday how to punch that into your calculator. You take the logarithm of the big number that you're trying to evaluate, and you divide it by the logarithm of the base, which would be a 2. And now you'll be able to get the answer. So we'll be able to use a calculator to figure these out. So let's check this one out. I want you to see that it truly works. That's how logarithms work. So log of 7, making sure you finish off the parentheses, divided by log of 2. Now, I think, what was I checking? I wanted to see 2 to some power is 7. So to check this, if I take 2 and I raise it to that power by using the second negative, because that gets the answer back up, this better pop out as 7, or I did something wrong. It's 7. Okay, Hunter? All right. Happened before, one of those type of things? Okay, good. All right. So, what we just did absolutely works. And like it says, if m and n are positive numbers, we're just going to take the logarithm of both sides. Now, what logarithm are we going to use? Did any of you use ln to do yesterday's assignment? No. You know, we're more comfortable with log, with the logarithm-based 10. You can, but it makes more sense to just use the log when you're first learning. So now, here comes one of those problems. We've got 15 and 285. To be honest with you, I probably wouldn't even try to find a smaller base. I don't want to mess with 285. 15 to something and get me 285. So instead, I start thinking, all right, I have to gain access to that x. 15 is in the way. While that 15 is there, I can't get to the x. So I'm going to have to take the logarithm base 15 of both sides to do that. Now when I do that, fantastic news over here. Logarithms and exponentials are such pure inverses, they just drop off. On the other side, I'm going to have to do a little change of base, like you learned yesterday. Log of the big number you're trying to evaluate divided by a logarithm of the base. Only this one won't be done when we punch that in, because we're still going to have to divide by 3. But still, it's just a punch it in thing, so that's good. So we'll figure out what this mess is, and then we'll divide it by 3. And that'll give us our answer. Now, let's see what we get. Log of 285, parentheses, divided by log of 15, parentheses, gives us that, divided by 3. Now, we would love it if we could write down all of this answer, because that would be exact. We know that's the answer that's going to give us what we wanted at the beginning here. If we put 0.6957633712 right here for x, this is going to work. But history tells us that people got really tired of writing down all those decimals. So what they decided was to go to 10,000th position. That's the 4th decimal position. So they typically wrote this as 0.6958 because there was a 6 in that next position. And we're going to stick with that. We're not going to buck history. We're going to say, yep, 4 decimals, good enough. It'll be a little off when we go to check it, but we know that. We can't write down every number the calculator stores anyway, because it only shows us 10 at a time, even though it has more numbers in there. So So now, got it to A looks to be a fabulous problem for you and your partner. Give that one a try. And that means we're going to take logarithm base 5 of both sides. Oops, didn't finish off my G before I started on my 5. There we go. Because what that does is it gets rid of this. And that lets that 2x drop down so that we can solve for it. And then over on the right-hand side, this is just going to be change of base formula. Log of 130 divided by log of 5. And once we get that answer, we'd have to divide by 2. And what that come out to, everybody? 1.5122. Etc., etc. So have to get rid of that base. We do. We need access to the x, and the only way we can do that is by getting rid of the base. So B said, why couldn't we do the same thing we did in problem 1 to problem 2? Tell your partner, why couldn't we do the same thing we did in problem 1 for problem 2? All right, if we have, in both cases, we had a 15 and then we had a 5. There is no nice number that we can raise them to get 130 and 285. So there isn't a nice base that we can raise to a power, and that's what we would put. There isn't a common base. That's the fancy way for saying, yeah, there's no base that's going to work for both of these. It's not there. If it were, I would have solved it, but it isn't. So we can use logarithms. So then people will always ask, hey, if we went back to problem 1, could we just use this?
No.
We could, but it would be much more complicated. So it's easier for us if we see the common bases to solve those that way. Alrighty, this one says, how about if we want to solve this exponential equation? Alright, so let's try common bases. 4 is pretty obviously 2 squared, right? 2 to the something is 6,000. Anybody know that one off the top of their head? So then we won't do it that way. You know, we want to use something that would be something helpful and easy to do. So how would we get rid of the 4? Log base 4. Jackson, put the phone away. So this will be gone. It's been warned. Next time it'll be. Now you just did this in 2 problems with your partner. So what do we do next? Log 6,000 over log of 4. Anything else you'd have to do to get the answer? Divide it all by 3. Well, let's find out what that is. Log of 6,000 parentheses divided by log of 4 parentheses, and divide that by 3. 2.0918. Here it is. Again, it is checkable. We can go back up here and say, okay, I need 4 to the parentheses 3 times the answer I just got, power. And this better come out to 6,000 or we did something wrong. Perfect. 6,000. So checkable. So with your partner, go after 3A and B. Well, a lot of you are looking like experts by the time I got to you. You already had your answers down for these. So we're making the bases match in A. Nothing weird about that. It's just like the other problem we did. So 0.8588. Now, nobody asked this, and in other classes, typically somebody has raised their hand and said, can we do this with decimals? Sure you can. Calculator will do it. Calculator doesn't care that it's a base of 5.2. Couldn't care less. So 1.2114. 4, got it. 3B. So anybody need to punch it in again to make sure everything was going well? I went around once already, but looks like everybody was doing just fine. Alrighty, so well, that looks like a good place to stop and check on things. How you feeling? 43210. Solving our exponential and logarithmic equations. As long as you have a calculator, it's good, right? Yeah, using that change of base formula. Alrighty. Well then, the way you guys were going, you ought to be able to finish this. No. Before you get out of your job. Thank your partner for your wonderful knowledge.